Thank you for the very kind introduction. It was the vibration engine of an iPhone, not a vibrator, but anyways. I'm going to talk about Hawkeye, which is our automated approach to basically find symmetric cryptographic implementations in gate-level netlists. This is a joint work with two people from Cryptography, Gregor Leander and Lukas Stennes, and my supervisor, Christoph Paar, from Ruhr University and from Max Planck. So let's get started. So you might all have some understanding of symmetric cryptography. I kind of try to align this a little bit here just to get the basics of why this stuff works that I'm going to show you. So we start with a standard example. In this case, we have two elephants, Alice and Benjamin. They want to communicate with each other. And since I couldn't find out what the English translation of the sound is that elephants make, I stuck with the German one. And we just assume that some other elephant, Charlie, wants to listen in on what they have to say. But luckily, they encrypt their Toureuse, and Charlie cannot really listen in. And they do this by sharing the same key on both ends. So Alice and Benjamin, they have the same key, and they can encrypt the messages on this channel. If we switch to more practical applications, we might have Alice in a tank somewhere on the front line. We might have Benjamin on a radio somewhere, and Charlie on the other side of this who wants to listen in for practical reasons. So still, Charlie can't really listen in because of the encryption, but what if he really, really wants to? So people still tend to use bad cryptography in proprietary designs and commercial applications, but also in more state ciphers, stuff like this, that have not been as tested as other public ciphers might have been. So there's hope for Charlie, but the problem is the crypto might be secret. It might not be public. You cannot really analyze the algorithm. So you must recover the algorithm somehow to then perform analysis on the crypto stuff. How would you do this? In the most boring example, you would just read public documentation, papers, standards, patents, whatever. I think Lukas or another group, they recently discovered a document that standardized a NATO cipher, which was not too great. And then they, through reading the document and analyzing the cipher, found attacks on the cipher. So this is kind of easy / boring. You can start right at the algorithm. You don't have to find the algorithm. But this is not always available, of course, as I just said. So you need to do some reverse engineering. You can do this for software. If you're lucky, your crypto algorithm might be implemented in software somewhere. And there is actually previous work on this that has been published at Usenix by Maya et al. Called Where's Crypto? So this is a paper that automates looking for cryptographic implementations in software binaries. But for hardware, there's not really anything around that is specialized for this. So this is where our tool Hawkeye comes in. Thanks to ChatGPT, we have a nice picture here. And Hawkeye, just to place Hawkeye in the chain of hardware reverse engineering, basically, I'm briefly going to introduce how you would go from ASIC to netlist and further, and from FPGA. So starting with ASICs, you would usually have to decapsulate, you would have to delayer, you would have to take images of all these layers that you have then prepared for you. You would need to process these images, and then you could, in the end, potentially extract a netlist. This is a very, very time-consuming and error-prone process. You can talk to Olivier if he's around, I don't know. Yeah, perfect. He will tell you more on this. And then if you've got the netlist, you can start with analyzing the actual netlist. For FPGAs, this is a little bit simpler, and this is because why our group usually goes for FPGAs. You just need to find the bitstream somewhere that configures the FPGA. You need to understand the bitstream, and then you can convert bitstream to netlist again, and again start working on the netlist. Hawkeye operates only on the netlist, so we don't do the other stuff. So we ignore the complex technical stuff and start with the fun stuff. All right. Little introduction on how cryptography is implemented in hardware. So if you want to learn more about AES, my supervisor has awesome videos on YouTube. I'll give you a quick slideshow on the most important stuff that we need today. But if you want to learn more, the internet is full of details. Looking at AES, the Advanced Encryption Standard, standardized a bit more than 20 years ago now by NIST in the US. It basically takes a plain text that we want to encrypt, so the information we want to keep secret. It takes a key that is also under 28 bits long, and using plain text and key, and it encrypts the plain text to a ciphertext that the attacker cannot read anymore, cannot access anymore without knowing the secret key. as long as a cipher AES is secure. And what we are hoping for is basically finding ciphers that are not secure that we could attack. Okay, looking into AES, we have some key schedule, key additions, and then a couple of rounds, 10 rounds in total. And all of these 10 rounds basically do the same operation all over again. Last round is a little exception. And then this key schedule is just responsible for taking the key and generating a fresh round key for each of these rounds. So nothing too important for us, at least in our setting here. So we are focused on these round structure. And if we look into the rounds, we see that we have the old state, computational state coming in before the current round. We have the new state going out after the current round. And we always have round keys going into the block that is being operated on. So the first step is something called byte substitution. Then we have an operation called shift rows, mix columns, key addition. Key addition is quite obvious. The rest we'll look into a little bit more details soon. Just like one minor remark here, this byte substitution step is a non-linear operation, which is important for security reasons. And then these shift rows and mix columns operation are linear operations. So they have a rather simple structure. And if we now look at how we would implement this stuff in hardware, we in our paper considered two options. I know there is dozens more, and you probably know better about most of them than I do. But we focused on pipelined and on round-based implementations. And for the pipelined implementations, the idea is basically to implement each of the 10 rounds individually in its own like hardware circuit. So we have 10 implementations of the round functions, and there is state registers in between that hold the state for a cycle, kind of. So you could then clock this entire thing, and it's called pipeline because you can, during every clock cycle, you can put one plaintext in, and it will propagate over the course of 10 clock cycles to the end, but you can encrypt basically multiple plaintext in parallel at different stages of this design. Of course, this wastes a lot of area for the benefit of performance. Quick remark, the state registers are, of course, implemented as flip-flops, and the round function is going to be combinational logic and or XOR whatever gates. And the data path, or how the data flows through this design, is basically from left to right. For round-based implementations, we have a way smaller construction. We have the round function only once, and we have one state register, and every clock cycle, the next round will be computed and then written back to the state register. So we have this loop. This means that we cannot encrypt as many plaintexts at the same time, but it also means that we need probably 10 times less area for the implementation. Okay, and over here as well, like flip-flops in the state register, combinational logic for the round function, and then the data flow is this loop structure instead of from left to right. Okay, what makes this special? Which properties can we kind of abuse for our detection algorithm? So the first one is that the flip-flops in the state register only really influence other state registers and other ciphertext output. So if you look at this over here, if you look at the first state register over here, I might switch to laser pointer. All right, the state register over here, these flip-flops in here only lead to other state registers and in the end to the ciphertext. There is no branching out of this construction. So if we would branch out with intermediate states of the encryption, this would be a huge security problem. So we can safely assume that there is no other connections from the state register going anywhere. And the same is also true for the round-based function, just that like it immediately leads into the ciphertext and then back into itself as well. The second property that we want to abuse is the state register flip-flops and the ciphertext flip-flops are distinguishable. You have to believe this. I won't show the details here. You can read the paper if you like. And then the round function only depends on plaintext, round keys, and state machine signals. Like, as for example, as you can see here, the state machine would, for example, control the slight difference you have in the last round of AES. And you have a very limited set of inputs, and you have a limited amount of options where like the state is flowing to. And there's a fourth property, but to fully understand, let's briefly go over the AES operations one by one. So this is the AES state. This is 128 bits in one byte blocks, basically. This 4x4 grid, 16 bytes, is basically your plaintext at the beginning. And now assume that within, we send in one plaintext, and then we want to send in another one, but in the other one, we change one bit somewhere. So there is 1 bit difference between the plain texts, and now we want to understand how this difference propagates. Okay, how this different, or where this difference ends up in the end. So the first operation that we do is subbytes, and this takes care of propagating this 1 bit difference to an entire byte, because if you look at subbytes, and this is kind of important for later as well, it's implemented as S-boxes, 8 to 8-bit S-box, meaning we have an 8-bit lookup table. 8-bit value going in, you look in the table, replace the input value with the output value that's in the table, and then you have your new byte for this block, basically. And this is also why if you have 1 bit difference, you look in a different table entry and you'll have an entirely different output of this subbytes operation. Next operation is shift rows. This, as the name suggests, just shifts rows in the state. For example, the second one to the left. Then we have something called mix columns, which mixes all fields in the column. So the difference will propagate through the entire column. We do have another, I think, subbytes, yes, which does not, I mean, the bytes change, but it doesn't propagate any further. Then we shift the rows again, and now you see that each row is shifted by a different amount. And in the next step, we have mixed columns again. You can probably guess what happens, like the changes all over the place. And this basically translates to this avalanche effect, meaning that if you look at one flip-flop in the first state register, after a couple of rounds, it will be connected to all other flip-flops of another state register. So you can, from one flip-flop, you can always reach in at least one of, or many of the other state registers, you can reach all the flip-flops in this state register. And together, we can use all these, like 4 properties for structural candidate search. And the problem that we're facing here is that this netlist where the crypto is in might potentially be like huge. So that can be, and crypto might be only like a really, really small part of it. And so we want to have something that's fast. And usually if you want something that's fast on netlists, you've got to go for structural analysis, like graph-based analysis, where you use graph algorithms. Otherwise, you'll run into timing issues. If you do functional stuff, as I'll show you later, this can take days, weeks, months, whatever. And we don't want to waste too much time on this. Okay. Once we have figured out candidates that kind of look like crypto, we can analyze them in a bit more depth and do this functional approach where we actually look at the Boolean functions that are implemented by the combinational logic. So you combine all these AND, OR, XOR, whatever gates, or the LUTs of the FPGAs into one big Boolean function that describes the round function. And then you would go ahead and analyze this round function to find out what is actually implemented here. And ideally, once we have the state registers identified with the candidate search, we can just cut out the round function in between the registers. We can start analyzing automatically, and we can also, if it features S-boxes, not all ciphers do, there's some that don't, but if there's S-boxes in there, we can cut them out automatically and then analyze them even further. So let's go into a bit more details on this structural candidate search, because it's kind of the core of the entire algorithm. Everything else is nice to have, but the main advantage of this is that I press a button, and a couple of seconds later, this tool will show me crypto is here, and then I can look there. So this is the important stuff. And the first step we do for this structural candidate search is some pre-processing. So if we look at this very small netlist over here, we see a couple flip-flops, and they are connected through combinational logic. There's AND gates in there, some inverters, some OR gates. So some combinational logic, and we get rid of all the combinational logic because at this stage, we are not looking at it. So we're just interested in the flip-flop graph, and we replace every combinational gate in there by basically a connection. So you see, for example, like up here, we had those couple of gates, and on the next slide, we just replaced them with one connection. So we just want to see how the flip-flops are connected with each other, but we don't care about the combinational logic at this point. And then in this example here, each of these boxes would be a flip-flop, and the edges you see would be connections between the flip-flops. So now we are just analyzing this flip-flop graph. It's way smaller than the entire netlist, so this is also another good speed-up opportunity for us. And we just randomly start at any of the flip-flops. In the end, we will actually start at every flip-flop of the netlist for this analysis approach. But for this example, we just start here with this one, and then we look at the successors of this flip-flop. So we look at what this flip-flop is connected to, and we'll find that it leads to 2 other flip-flops. And then if we look at the successors of these 2 other flip-flops, we find 4 other flip-flops. and then maybe 8 in the next stage. And this is a very small example. This is why we're ending here. We find 8 again. And you see that this saturates at some point. And this is because of the properties that we've just talked about. So you only go from state register to state register, and from state register maybe to ciphertext register, but you don't go anywhere else. So you are stuck with your registers, and you can differentiate between state and ciphertext. So if I stop propagation at every ciphertext register or every ciphertext flip-flop, and only assume that in this final set of flip-flop that I've discovered, there's only state flip-flops in there, then this stuff will saturate because my register in this case only has 8 bits. In the AES case, it only has 128. So at some point, these sizes won't grow anymore. And if we find that they are the same over a couple iterations, then we just declare this thing to be a candidate. And of course, the structure can sometimes also be observed for other stuff, like counters like to do the same thing, same for some state machines. But the neat thing is that we can, for crypto at least, we can usually assume that the candidate we found is at least bigger than 64 bits, while for counters, this is not often the case, at least in the netlist we've been looking at, and especially also for state machines. So you can usually differentiate by just the size, and otherwise, crypto is always a power, or the state size of crypto is usually a power of 2. If your size doesn't look nice, it's probably not crypto. Okay, once you've identified this candidate, you can do functional candidate analysis just by basically cutting out the logic in between the 2 state registers that you've just found. And maybe just to recall, we look at pipelined and at round-based. So at a pipelined implementation, this would be one state register and this would be the other one. In a round-based implementation, those 2 would actually be the same thing. So those 2 registers would actually be the same register in hardware. Okay, now we just cut in front and behind the registers, and we get the round function. And if we look into the round function, we see these S boxes. They're usually the first thing that's being computed on the register content. And then you have this linear layer, which in the case of AES was basically this shift rows and mixed column thing. And the S boxes have kind of a unique structure because of this non-linearity. This is something that you don't often see in hardware for other purposes. So if you see it, if you find it, you can be rather sure that this is actually cryptography. The linear layer, not so much. It can be implemented as purely XOR operations. And it's usually not that complex. So we tend to just look at the S boxes here. And the idea is then that we know S boxes from public documentation, from standards, from whatever. And we have a database of S boxes. So we have AES, we have present, we might have Kuchnicek from the Russian AES counterpart. And we might have all these S boxes in our database. And then we just check the S box that we extracted from the circuit against the database using some smart algorithm that our crypto people found somewhere on the internet in another publication. And then you can basically match against this database, and the algorithm will, even for larger netlist, in a couple of seconds or minutes tell you this is AES. And then, if you know that this is AES, you're probably not interested because you're looking for interesting ciphers that you can break. But this is also a good hint that saves you some time in your analysis. One quick remark here. The problem that might arise here, which is also one of our limitations, is that other ciphers might reuse the AES S box, or for example, the present S box. So some proprietary cipher could still use the AES S box, be flagged as AES, but not be AES. So you need to be a little bit careful here and probably still look into the candidate that you found here, but at least you know what the S box is at this point. Okay. And having the S boxes also allows you to cut out the linear layer in theory, although we didn't really implement this at this point. Okay. We presented this initially at a mathematicians cryptography conference, and they like proofs. We can't prove any of this. It just works, but that's not enough for them, so we needed to evaluate. And we actually evaluated on actual hardware reverse engineering due to the timeline of academic papers was not really an option. We couldn't open up a chip, extract the netlist, pay a lot of money for this because we don't have the machines, and then work on the probably erroneous netlist. We also couldn't really find an FPGA that would have crypto in it. So we just synthesized our own hardware designs, or basically open source designs we took from the internet, The first one was OpenTitan as something that's actually relevant, hopefully. So it's kind of an industry-grade security chip designed by Google and other people. And it's actually quite large. It has a lot of crypto on there, so it's the ideal target to test our stuff on. We also had some smaller cryptographic accelerators in a smaller system on chip that we took from open cores, I guess, and some isolated cryptographic and non-cryptographic benchmarks to test like for false positives and stuff like this. Everything I'm talking about here is available online. So we have artifacts published with crypto that contain like our benchmarks and the scripts. Hawkeye is actually a plugin to our netlist analysis framework Hell, and this one you can find on GitHub. So you can just download, get a couple of coffees because building Hell takes time, and then execute the entire thing and try to find crypto in your designs. Looking at OpenTitan, we see that there is a couple, as I mentioned, couple of crypto stuff here that we would be interested in. So I've just put red boxes around everything that looks like crypto a little bit. And then we synthesize. We end up with an FPGA netlist containing 420,000 gates. We run Hawkeye on this MacBook actually in 44 seconds. And after 44 seconds, it will come up with a list of stuff that it has found. This is just the positive hits, like the stuff that we were interested in. It will also find some FSM here and a counter there. But most of what we found is actually interesting. The descriptions you see here are annotated after the fact by us. This is not the output of Hawkeye, sadly. This would be amazing. But for the AES, for example, it will find the S boxes. For present, it will find the S box. But you also see that there is lots of stuff on here that's not really documented by OpenTitan, which was fantastic, because then we had to start looking at code to verify what we've found. Okay. And as I said, we also tested on a bunch of just Cypher implementations where there was nothing else on the hardware core. And these are, as I just see, outdated stats. So the numbers are a bit better now. It's a bit faster. And I mean, don't read the table. The takeaway is it works. So it works for most SPN ciphers, ARX ciphers, and Feistel ciphers. If you don't know what that is, doesn't matter too much. It's not as great on like shift register based ciphers, like Trivium, for example, or Catan. Those are those have a different structure. They usually don't have this round structure. Sometimes they can be implemented in an optimized way that kind of looks like a round structure. Then we find it. If they are not, we won't find it. And of course, I mean, this is about symmetric crypto. We usually can't find RES implementations and stuff like this. But on the other hand, RSA is just going to be like a huge multiplication unit somewhere. So this is also quite easy to spot, I would assume. Yeah, and then also at the bottom, we tested on some non-cryptographic design, some CPUs, some magic digital signal processing stuff that I don't understand. And it shows rather good results. So we have few false positives, but not too many to worry about. Okay, quick recap or summary of the entire thing. Bit ahead of my time, I guess. So we, as I said, like we're optimized for SPN, ARCs, and Feistel. This was the goal from the beginning. We wanted to find those. We sometimes also find others, but that's not reliable, so don't rely on it. Detection is fast, usually at most a few minutes, even for the large design of OpenTitan. It takes like 40 to, if this one has a bad day, 60 seconds. And then for future work, of course, I mean, I said we didn't cover shift registers, so it would be great to cover shift registers, and we might have a master thesis on this soon. We completely ignored side channel protections. This is also something we should at some point consider, but we believe that this will not really be a hurdle for the algorithm. Currently, it won't find it just because of some of the way we implemented it, but we assume that this is still possible to find, even if ciphers are side channel protected. We would like to actually find what like our target was, unknown cryptography. And this is also my kind of call to action. If you have hardware devices with crypto in them, that could be published in the end. I mean, I'm academic. I need to publish. And this is usually the big problem with this. Then please reach out to us. Yeah, and this is the end of my talk. If you want to know more, as I mentioned, Hawkeye is a published paper at Crypto. You can find the paper at this QR code. You can find the open source implementation of Hawkeye as part of Hell at this QR code. And I quickly asked Antrich whether I could abuse this opportunity for a bit of advertisement. We have a workshop on hardware reverse engineering in Bochum next year, March 17 and 18. This has been going on for 2 years now. Last year we had like 130 participants. This is going to be on ASIC reverse engineering, FPGA reverse engineering, netlist reverse engineering, all kinds of stuff that might be interesting for you. This is not an academic workshop, not purely. There is people from industry, government, academia. Actually, only very few people from academia usually, but still, if you want to attend, you can find more information on the website. Registration and other stuff will open later this year. All right, questions?
Can you expand a little bit on the experience with OpenTitan and how hard and what kind of resources you needed to implement that? And did you consider Calyptra as a target?
We did not consider Calyptra. On OpenTitan, we are kind of lucky to have an implementation of OpenTitan on FPGA already. That was configured without any side channel stuff. I mean, you can enable side channel stuff on OpenTitan. But again, like we then just loaded this thing into Hell, pressed like go, and it found the stuff. So there is not much involved after like implementing Hawkeye. It had some issues here and there with the S-box identification. So on some of the candidates, it timed out. SHA-3 is a prime example because this has a 1600-bit state, and this was a bit too much for what we wanted to do. But on those, we just had a threshold, and then it doesn't crash anymore, at least.
All right, more questions here in the back.
So, thank you very much for the great talk. One question, did you go totally down to the bitstream and then reverse the bitstream with Hell? Or did you just do with Fuses or Xilinx synthesize run and then...
Yeah, thanks for the question. We didn't go from bitstream to netlist, so we saved the Z part and the headache that would have been involved with it. We synthesized, or the OpenTitan was previously synthesized with Xilinx Vivado. I don't think anyone has managed to actually pull this off with Yosys yet.
That is sad.
But yeah, it was Xilinx Vivado, and then we just exported the netlist from Vivado. This is also helpful because Vivado leaves names in it, and we needed to check our results somehow. So we found crypto, but now we also needed to know that it was actually crypto, and just having the name AES written at the gate is easier then. We didn't use that for finding it though. So it was, we didn't, like, Hawkeye doesn't scan gate names.
Maybe one last question to that. So would you expect that after placing and routing the design, having a bitstream and then recovering the bitstream, that the results would look similar or not? So would you expect optimizations to happen that probably the S boxes would be quite recognizable, right?
Yes, I mean we actually gave a training on like finding crypto stuff the last 3 days, and we did this from bitstream to netlist and then netlist Hawkeye, and it works. The thing is that this very much depends on the bitstream reverse engineering tools you're using. We relied on this project X-Ray and their Pheasant to Bells tool that would convert bitstream to netlist again, and it has some errors here and there, so these can impact detection. But usually, if your tooling is correct, this works on netlist recovered from bitstream, similar to the stuff that you export from Vivado. It's the same. It's like it should be the same. Should.
Thank you very much.
You're welcome.
Any more questions? We have so much time. Please ask more questions.
I'm sorry.
Hi. Thanks for your talk. If you were to write a symmetric crypto algorithm and you don't want it to be detected by your tool, how would you do that?
That's a very good question. We have been asked before. No, like the problem is if you follow these known guidelines, like for cryptography, you always, I mean, for SPN ciphers, you always have this structure. You can't escape it. Currently, you can defeat our tool if you implement side channel protections, but if we target side channel protections, I mean, this is going to be a back and forth. as is for any kind of obfuscation. Crypto always has structure. It needs to have structure due to the mathematical stuff that's underlining, that's underneath. So I think it's going to be hard to defeat stuff like this. Even if you've come up with some fancy new crypto algorithm that does something different, then I can probably just write another detection tool. Yeah.
One more question here.
Thank you for the talk again. What is the problem with side channel protections? I was thinking, since as far as I know, most side channel protections rely on some source of entropy, some randomness. Couldn't you just follow where the randomness is going if you know where the source of randomness is and find the side channel protected algorithm?
Yes. This would require another approach. We just implement this approach now. If we would find side channel stuff or defeat side channel stuff, we would need to implement another algorithm as part of Hawkeye that targets those. There's also side channel protections if you do masking and stuff that introduce more flip-flops, more registers, in between or in the combinational logic basically. And this would currently pose problems to us. But if we know about this, we assume, we haven't tried, we are also not experts on side channel stuff, then we assume that we can still defeat it. We just need to spend the time.
Right, any more questions?
Should have made a longer talk.
I'm sorry to be off topic, but since we have time, can you please elaborate more on Harry's workshop? Because on site there's just too little information.
Yes, the workshop is going to be mostly talks that are contributed by the community, so you can actually hand in talks and present. Slots are going to be 20 minutes, I guess. Call for abstract is going to open soonish. Registration is usually, I would assume registration will be around €200, 2-day event in Bochum. There's a nice dinner on the first day. And there is going to be a lot of socializing. We will have some speed dating stuff after coffee breaks maybe. There will be discussion opportunities. You'll have the dinner. All that kinds of stuff. So the idea is to bring all the experts in the field together. This initially started as we wanted to gather our friends and family in Bochum, and then 90 people showed up. And last year we had 130, this year maybe 150, I don't know. But it has grown to an international audience, so it's not just people from Germany. Basically the entirety of Europe is present. There's lots of government people, there's lots of industry people, and a few academics. This is not a very academic topic usually. We are not in competition with too many groups internationally. Those that do research on this will also be present. So it's a big mixture of everything. But we usually don't offer trainings with it or applied workshop. It's going to be the talks for the content of the workshop, and then mostly networking around that.
More of a comment to the obfuscation question before. There was a few years ago at the Design Automation Conference was a nice talk about how the DARPA is basically sponsoring this cat and mouse game for circuit obfuscation, because of course every missile needs its circuit that controls it, and they are basically sponsoring with a lot of money those obfuscation games.
Yeah, you have the same kind of thing with logic locking. There is people proposing new logic locking schemes, and there's other people breaking them again, and this has been going on for, 15 years maybe, and there is no solution yet. So this is how obfuscation kind of works, I fear. It's always whoever has the more money and time will win this game.
Right, I think there's no more questions. Otherwise, you can talk to the speaker later. I'm sure he'll be around.
Yes.
So let's thank the speaker again with a round of applause.